Last speaker this morning, it's a pleasure to have Raphaël Forien going to tell us about fluctuations in stochastic bistable traveling waves.
Thanks, Julien. It's a pleasure to be here, and I'd like to thank the organizers for this opportunity to be here and to present this work, which is an ongoing work with Sarah Penington and Alison Etheridge on stochastic bistable traveling waves. Our original motivation when we started this work was the study of hybrid zones, which you might have heard about before, if you've seen a talk by Sarah or Alison. And hybrid zones, the simplest setting in which you see hybrid zones is when in a diploid populations, we have one gene with two alleles, capital A and little a, and heterozygous individuals have a disadvantage over both types of homozygous individuals, so that the fitnesses of the three genotypes are given by these is of this form. And if we start from a spatial configuration where all capital A individuals are on one side and all little a individuals are on the other side, we expect that at the interface between these two regions, we're going to find some heterozygous individuals because there is some random mating in the population. But these guys are not as fit as the others, and so they will not expand and the hybrid zone will stay narrow. And if the two selection coefficients are equal, then it should not move too much, because it's the same advantage on both sides. But if the selection coefficients are different, then the hybrid zone might move to one side, because the fittest homozygous types is going to invade the population. And we want to understand how this happens in natural populations and what's the effect of stochasticity on these kinds of populations. And I'm going to start with a really complicated model and simplify it as we go along. And the really complicated model uses the spatial lambda Fleming-Vio process framework that was introduced by Nick Barton, Alison Etheridge, and Amandine Weber. And here's how the model works. We fix the two selection coefficients, S1 and S2. We fix a radius R and a parameter U, which is between 0 and 1. And we're going to keep track of the proportion of capital A allele at each spatial location and at each time. So when we have a homozygous individuals, it counts for 1, and a heterozygous individuals counts for 1/2 for the proportion of capital A allele. And we're going to draw reproduction events at random at different locations and at different times. And there are going to be three types of reproduction events: neutral reproduction events and selective reproduction events, which are going to select either in favor of capital A individuals or little a individuals. And these events are all Poisson random, given by the points of Poisson random measures on R plus times RD. So we have a time and a location. And for example, if we have a neutral reproduction events happening at time t at location x, it affects the individuals which are in a ball of center x and radius r. And what we do is we're going to pick an individual that is going to reproduce. And an individual has two copies of the gene, so we're going to pick two copies at two locations according to the proportions right before the reproduction event. So this gives us two alleles K1, K2 that we picked at locations Y1 and Y2. And then we're going to replace a fraction U of the population in the ball by individuals with genotype K1, K2. And so the new proportion of capital A allele after the reproduction event is going to be 1 minus U times the proportions right before the event, because this is the contribution of the individuals who survived the reproduction event, plus U times this ratio here, which is just saying that we count 1 if we're adding capital A individuals, we count 1/2 if we're adding heterozygous individuals, and we count 0 if we're not adding any capital A allele. So this is neutral reproduction. And for selective reproduction events, instead of picking one potential parent, we're going to pick two individuals. So two individuals means 4 types. So we pick 4 locations and 4 types at these locations according to the proportions right before the reproduction events. And with these 4 types, we form 2 genotypes, K1, K2, and K3, K4. And if one of these 2 genotypes is the one that we're selecting for, then this guy is going to reproduce. If none of them is of the right type, then we just pick one at random. Okay, so it's a reasonable way to bias the reproduction in favor of the homozygous individuals of this type. And the way we update the allele frequency right after the reproduction event is just as before. We just changed the way we choose the reproducing genotype in the population. So here's, for example, a simple simulation in one dimension, where here I'm just plotting the proportion of capital A alleles. And you see that as I add in more reproduction events, the line gets more wiggly and the interface develops. Okay, I'm not going to run it for very long. So it's quite a complicated model, and we can't say much about it as it is. But what we can take is scaling limits of this model to understand how it should behave in some regime of the parameters when some parameters are small. We're going to assume first that the parameter u is small, so it's like u over n, and that the selection coefficients are also small, like delta n squared times some fixed coefficients, where delta n is a sequence converging to 0. So it's a weak selection, and the fact that u is going to 0, you can think of it as taking a large density limit, because at each reproduction events, an individual produces some number of offspring, and the fraction of the population represented by this offspring goes to 0. So it's a large population limit. And we're going to rescale space and time so that we see something interesting happening. And the right way to rescale this is to look at spatial scales of order 1 over delta n, speeding up time by a factor n over delta n squared. Okay, it's something that you can convince yourself of quite easily. And we have this result of Etheridge, Weber, and Yu, which was proved for a different kind of selection mechanism, but it's quite easy to adapt to this one, where if this quantity here tends to infinity and the initial condition of the rescale process converges, then the rescale process Pn of t converges, at least on compact time intervals, to a deterministic function ft, which solves this reaction-diffusion equation, where we have dt of f equals something times the Laplacian of f, plus a reaction term here, which I'm going to say more about in the next slide. Note for now that there is this condition that n delta n to the 2 minus d tends to infinity, and n is going to infinity, delta n is going to 0. So when d is equal to 2 or larger than 2, this is automatically satisfied. But when d is equal to 1, there is an assumption here that you have to make to obtain this deterministic limit. Okay, so here I'm going to betray my origins and put a 1 in front of the Laplacian. You can rescale space and time easily to get 1 in front of the Laplacian. And the reaction term that you get is P1 minus P times this function, and you can rearrange it easily and split it into a symmetric part and a Fisher KPP part. And by symmetric, I mean that if you integrate this first part between 0 and 1, you get 0. And alpha here is S1 minus S2 over S1 plus S2. So alpha equals 0 corresponds to S1 equals S2. Alpha equals 0 case here is the red curve below. So this is the symmetric part of the function. And you see that it's negative below 1/2 and it's positive above 1/2. And when you increase alpha, you still get this picture that it's negative close to 0 and it's positive close to 1, but there's a shift. And as you cross the threshold 1, you get a positive function everywhere, but it still does not satisfy the Fisher KPP condition, because the slope at 0, I mean, if you follow this, the function is above its slope at 0. And in order to satisfy the Fisher KPP condition, you have to reach alpha equals 2. And for the rest of this talk, I'm going to be concerned mostly about the green curve here. So negative part close to 0 and a positive part close to 1. This is the bistable case. I'm going to say maybe a bit about the orange curve at the end. And how can we see that this is the right form? Well, when the frequency of capital A alleles is quite low, even if there are selective events in favor of capital A individuals, it's actually quite unlikely that during the reproduction event we pick two types, capital A, and we form a capital A genotype. And so these selective events are not that efficient when the frequency of capital A alleles is too low. So this is why, and on the other hand, the selective events in favor of little a alleles are quite efficient, because it's quite likely that you will pick at least one little a individual in a reproduction event. So this is why the frequency of capital A is going to 0 when it's close to 0. And on the other hand, it's going to 1 when it's above this threshold here. And yes, from now on, I'm going to assume that I'm in one spatial dimension. And for this, we know from works in the 70s and the 80s that, so for alpha between 0 and 1, and so that's the bistable case, there is actually a unique traveling wave profile, which with a very bad choice of notation, I'm going to denote M. And so there's a unique M and C such that ft of x equals M of x minus ct is a solution. And if f naught looks like a front, so if the initial condition looks like a front, and actually it looks like a front here is quite easily satisfied, right? It has to be below some threshold near plus infinity and above some threshold near minus infinity. Then ft of x minus this shifted traveling wave profile is going to converge to 0. And notice here that the shift is just the deterministic speed plus a constant. There is no logarithmic term, no Bromson correction in this case. It's just somehow a stronger form of convergence in this bistable case here. And M is actually explicit for this particular choice of the reaction term. It's 1/1 plus e to the x with some constant. And the speed is proportional to alpha. So, okay, we have a deterministic approximation of our stochastic model. And the deterministic approximation predicts that the hybrid zone will move at some speed to the right. And it's quite, okay, this is what does the deterministic system, okay, it quickly converges to the traveling wave profile and then it moves. What about what happens in the stochastic? Well, it's a difficult question, and it's a difficult question for this very discrete process with lots of reproduction events. And I'm going to use a simplified model that we can derive in one spatial dimension in the following way. So this is the scaling that I had before, a small u, a small s, and the rescaling of time and space. And I'm going to assume that I'm in one spatial dimension and delta n is actually 1/epsilon n. So that the quantity that had to tend to infinity in the previous theorem is now equal to 1/epsilon. So it might be big, but it's constant. In this case, if I let n tend to infinity, I get a different limit for my stochastic model. I get a limit v epsilon, which solves this stochastic partial differential equation, where if you remove the stochastic part here, you get the same equation as before. And so this noise here that is perturbing the deterministic equation has this epsilon factor here times square root of v1 minus v dw, and w is a cylindrical Wiener process now too, so that if t here, and you have, so that's for any phi in L2, and there are some correlations which are, it's uncorrelated space-time white noise. So this is what the picture looks like. Okay, at the beginning it's a bit like the deterministic system. You see an interface developing, but the interface is a bit more wiggly than the other one, and you can see that it's actually, it touches 0 at some finite point, and it's stuck at 0 beyond that, and it touches 1 on the left. It's still moving, but you can see that it's maybe a bit more difficult to move than in the previous simulation. Okay, and for now, I'm going to stick with my equation v epsilon and pretend that the behavior of v epsilon as epsilon goes to 0 is the same as the behavior of the previous model as n delta n tends to infinity. And let me say a word first about previous works on these kinds of equation in a Fisher KPP case. So when f is proportional to p1 minus p, this equation has a very different behavior. And we know from papers in the 90s that there is a stationary front which moves at an asymptotic speed. So if you look at the rightmost point where the solution is positive, you divide this position by t and you let t tend to infinity. This has a limit c epsilon. And there is a famous conjecture by Brunet and Derrida, which was proved by Müller, Mitnick, and Castel in 2011, that this c epsilon has an asymptotic development where the main term is the deterministic speed of the PDE minus a correction which is proportional to 1/log epsilon squared. And that's a very strong correction. It's bigger than any power of epsilon. This comes from the pooled nature of the FKPP equation. The noise is perturbing a lot what is happening at the tip of the wave, and this prevents the wave from propagating as fast as it wants to. And this has a dramatic effect on the speed of the advance of the wave. And we're going to see that we get a different picture in the bistable case here. And in order to study the bistable case, I'm going to say first a few words about the case where alpha equals 0. So this is the symmetric case, the case where in the deterministic picture, the wave doesn't move. And there are some works on similar equations, but with a different noise term here, A, with this symmetric potential here. So there are two papers, Brasesco, Demasi, and Presutti, and Funaki, both in the same year, with different assumptions on the function A. And what they proved is that if you make some nice assumptions about the initial condition of your SPDE, then if you look at V epsilon at time t over epsilon, so you speed up time by a factor 1 over epsilon, it's always close to a shift of the traveling wave profile of the deterministic equation, but shifted by a random quantity psi epsilon here. And this psi epsilon converges as epsilon tends to 0 to psi of t, which is given by this simple stochastic differential equation. And so it has both a drift term and a noise term, which are both given as a function of the function A. We're interested in a slightly different equation where the noise term depends on the solution itself, but some things carry over. And there is a recent, well, it was recent when we started the project, by Birsu, Halacek, and Korolev, a work on the case where alpha is positive, where they define the position of the front as this integral, where if you think of V epsilon as an indicator function, then this is exactly the position of the front, right? If you have an indicator function moving to the right. So it's not an indicator function, but it's quite close. Then you expect, from their calculations, they show that 1 over t times the variance of this position should be proportional to epsilon, and there's an explicit constant d here, which already appeared in a physics paper, which I'm giving here. And there's also a correction to the wave speed that is proportional to epsilon. And this is what we're currently proving, and we have a proof that works for a certain range of alpha. I'm going to stay vague about, but it's alpha max is somewhere near 0.8 something currently. We're hoping to get to 1. Okay, the theorem looks a lot like the previous one. If you look at V epsilon at time t over epsilon, so you speed up time enough, and you look at it in the moving frame of the deterministic wave, so the frame moving at the deterministic speed, then it's always close to a shift of the deterministic traveling wave profile, shifted by this stochastic amount, this random amount psi epsilon, and this psi epsilon converges as epsilon tends to 0 to Brownian motion with drift. So it's an even simpler equation that you get in the limit. And if you
can you remind me what mu is?
it's I haven't told you what it is. It's something. Okay. We have an expression for it. And if you put this back into the previous equation and you undo the time change, what this tells you is that your solution to the stochastic equation looks like the front moving at speed c minus mu epsilon with and doing a Brownian motion around this position with a variance epsilon. And so it's very different from the FKPP case, because here the correction to the wave speed is much smaller. It's of order epsilon, and there is a variance of order epsilon around this position. And this comes from the fact that here we have a bistable wave. So actually, the process doesn't care much about what happens far from the bulk. And what matters are the fluctuations in the bulk. And these fluctuations are well described by Gaussian fluctuations, and this is why we can get Brownian motion in the limit and Brownian fluctuations. That does not mean that it's easy to prove, but It's the reason for that. And I will quickly tell you a bit about the strategy of the proof, and it all comes back to a paper by Katzenberger in the 1990s, where, okay, forget about the complicated SPDE that we had before. Suppose that we have just a simple diffusion in RD, which is of this form. It follows, we have a deterministic drift B of X plus Brownian motion with variance epsilon. And we define phi t of X as being the flow of the deterministic equation when we remove the Brownian motion. So the derivative of phi t of X is B of phi t of X. And we assume that if you let t tend to infinity, for any x, phi t of X converges to a point on this line here. Okay, so there's the deterministic flow corresponding to the drift in the SDE pushes you towards this linear manifold, which is just a real line. And there's a coordinate along this manifold, which is this zeta here. So if you start somewhere around there, what you expect x epsilon of t to do is to roughly follow the flow of the deterministic equation until it reaches the stable manifold. And then it should stay in the neighborhood of this stable manifold. And if you wait long enough, it will move a bit around along the manifold. And you can hope to describe how it will move along the manifold. And a nice trick to study how it moves along this manifold is to use this asymptotic coordinate zeta that we had in the previous slide to project the equation on the manifold. So if you define psi epsilon to be this zeta of x epsilon at time t over epsilon, well, you can apply Ito's formula to say what psi epsilon does. And you have three terms. The first one is coming from the deterministic drift in the SDE. The second one is a martingale term. And the third one is the Ito correction coming from Ito's formula. 1 over epsilon that we have in front of the first term comes from the speeding up of time. Okay. We evaluated x at time t over epsilon, and so the drift is acting much more strongly. So at this point, you might get worried because we have a very big term in this equation. But actually, since we chose zeta cleverly, this term is 0. Reason for this is that the gradient of zeta is orthogonal to the flow of the deterministic equation, because zeta is invariant along the flow. So that's why it's a nice way to project your process on a stable manifold. And so this term vanishes until you have two terms of order 1 in your SDE for psi epsilon. And okay, you still have x epsilon appearing in this SDE, but if you show that it's actually close to its projection onto the stable manifold, then you should get a convergence of psi epsilon to a limit, which is just given by a simple SDE on the stable manifold. And this is the SDE that you get. Of course, you have to assume that zeta is differentiable and nice enough. In theory, that's the idea. And in the paper of Funaki in 1995, which our proof is based on, he adapted all this technology to the infinite dimensional setting of the SPDE. So not a small work. So now instead of our diffusion x epsilon, we have the solution to our SPDE v epsilon that we shift in the frame moving at the deterministic speed. And if we look at phi t, which is now the flow of the deterministic equation in this moving frame, it's given by this equation. Using the deterministic results that we have, we know that for any suitable v, this flow converges to a shift of the deterministic profile. So now instead of a real line, we have all the possible shifts of the deterministic profile. And this is our stable manifold. And as soon as v is in a nice neighborhood of this manifold, we know that the flow converges to a point on the manifold. And so for any time such that v is still in this neighborhood, we can define psi epsilon as this zeta coordinate of the solution. And pretty much the same trick as before works and can be applied for this equation. And you need to show a few things. You need to show that the solution does not leave your nice neighborhood of the manifold for the times that you're looking at, and that the solution is actually asymptotically arbitrarily close to this manifold with the right projection, so to its projection on the manifold. And from this, you can deduce the convergence of the projection on the manifold to this SDE that we have. And psi t, so the limit of the projection, is given asymptotically by these two terms. So we have an integral against white noise. So this guy is a martingale term. And this is the Ito correction that we get when we project on the manifold. And so the first one is going to give you the sigma times Brownian motion, and the second one gives you the correction to the wave speed, so the drift in the projection. And you can see that, okay, I'm not telling you what d zeta here is, but we can compute some things about it. So it's fairly explicit. Actually, the expression for the variance is easy to compute, and this is the red curve here, depending on alpha. So as I've said, we've covered a bit of this range, but if you plot the function alpha, you see that it blows up when alpha equals 3/2. And this can be a bit surprising because the front is pushed up to alpha equals 2. It only becomes pulled at alpha equals 2, but the variance blows up before that at 3/2. And this was noted in this paper by Bizu, Halacek, and Korolev that I've already talked about. And they said, well, so up to 3/2, it's pushed fronts or fully pushed fronts, what they call fully pushed fronts. And it should always have this behavior of a variance of order epsilon and a correction to the wave speed of order epsilon. Between 3/2 and 2, it's a different behavior, and it's what they call semi-pushed fronts. And they argued that the variance should scale like some power of epsilon. Yeah, I'm losing the connection here. But, so in this paper by Bizu et al. In 2018, they say that you should expect this scaling for the correction to the wave speed. And I think this is right. It's, the notation is a bit.
Raphael?
Yeah.
Is alpha equals 2 is Fisher KPP, right?
Yeah, it's when it starts to satisfy the Fisher KPP condition.
So that's a condition of the. Okay.
It could be pulled before that, right?
No. Yeah.
Oh.
Yeah, okay, yeah. Alpha equals 2, it becomes pulled. Alpha equals 3, it satisfies the FKPP condition. And I must say, we don't fully understand what is going on at this stage. And even between 1 and 3/2, the proof doesn't work for good reasons. And there are, yeah.
No, use the mic.
Sorry. So the variance blows up at alpha equal to 3/2,
At 3/2.
but between 3/2 and 2, it's still pulled.
It's still pushed. It starts becoming pulled.
Okay. Okay. Thank you.
Yeah, I'm finished.
Okay, so it's time for a couple of questions. There's one here.
So the result, if I understand correctly, is kind of an annealed result, an average result, in the sense that you give the velocity on the fluctuations of the velocity on average, right?
Sorry, I can't hear you.
So I understand that the fluctuations you give are annealed in the sense that they are averaged over the W disorder.
The projection.
So my question is, suppose I condition on W. Okay, so there's nothing stochastic left. So that would be what I call quenched.
Yes.
So if I condition on W, do you have any idea of how much the front is behind? Like if there was no noise, we know it's logarithmic. And do you know what it would be here?
Well, the Ito formula gives you.
No, but you're conditioning.
Yeah.
So you know W. It's not that you, so maybe I misunderstand something, but the representation you have for the centering is not a functional of W, or can you write it as a functional of W? You just say in law, it's like a Brownian motion, but
Yeah.
you don't write it. So that's exactly an annealed statement. Averaged over the Brownian motion, the fluctuations are whatever.
Are you asking for a strong solution?
No, 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 no. No, I'm asking really for a quenched. What is a pool in quenched? So if I condition on W.
Yeah, there is we have a stochastic integral against W for the coordinated on the stable manifolds.
And there is no lower order term.
I mean, yeah, when we pass to the limit as epsilon goes to 0, we take limits inside this stochastic integral.
No, but the stochastic integral is measurable, so I condition on it. So you probably neglect along the way all sorts of other terms that are of lower order. Okay, maybe we discuss it.
Yeah.
Okay, I have several questions, but they are very much related. One is when alpha is less than 3/2, the coefficient, does it diverge when you approach 3/2? The prefactor. You have something proportional to epsilon. Does it diverge when alpha goes to 3/2?
Yes.
Okay, and then if you look at higher moments, you would find different critical values of alpha. If you look at the third or fourth cumulant of the position.
I haven't looked, but
okay, and okay, and even if you look at the velocity, and when alpha is less than 3/2, then you have it's linear in epsilon.
Yeah.
But then you go to the next term. Is it non-analytic or?
We don't have any idea of what the next term is.
You see, maybe there is a threshold where it becomes non-analytic.
I was just curious. So the fact that your noise is right Fisher prefactor, it's not really important, right? Like you could have had a different function there.
Yes. Yes.
So you
and
just
Beerzu and
change-
Halacek have a general. They have a functional that is something like square root of v times some function of v.
Okay, so you would just change the Ito's lemma and that.
Yeah, it would change the expression for the coefficients.
Okay, and a quick, maybe silly question, but in your original setup of what the motivation is, why couldn't S be bigger than 2? Like when you separated is there a reason why it couldn't be bigger than 2? Because there's a difference of the selections, the little S.
No, there is no reason.
Okay, and then you would just, it would be just KVP. I mean,
no, there is one because it's S1 minus S2 over S1 plus S2. And so, you have to change the model if you want to treat the case where alpha is larger than 1. We can for any alpha, we can have a stochastic model.
Right, alpha. I meant alpha is bigger than 2. Yeah. Okay. Thank you.
There are some questions in the chat.
I want to ask, does bistable means that you have 2 stable value? Like, what is the meaning of bistable?
Yes. Bistable means that essentially f prime of 0 is negative, so that the 0 is locally stable and 1 is locally stable.
Does that answer your question?
So, so actually, you can only have like 2 regions. One is a negative region around 0, and the other is positive region around 1. So you cannot have like other. Otherwise, you have multiple stable points. Is that true or actually not?
Yes.
So potentially, you can have multiple stable points, like more than 2. That way.
Then you have to worry that the traveling waves might separate. And
any other questions?
Yeah. Could you comment on the alpha max? So just a little bit what are the constraints that you have on it?
It's
I mean, you said it's roughly 0.8, right? It's not 0.01. So.
No, it's not ridiculously small. It's just that at some point we have to bound the square of the density of something. You apply Holder inequality and you see that you can choose the powers just for certain values of alpha. So I think we're just not clever enough and missing something that would help us prove it up to alpha equals 1. So it's not it's our failing, nothing interesting is happening with this value.
So is it because of the second moment argument, or I mean, why square of the density?
Yeah, it's because when you have the variance of something integrated against white noise, get the square of the function. This is where you also have the exponential weights coming up in the coefficients for the variance and the correction to the wave speed. So you have e to the alpha x, but when you square it, it's e to the twice alpha x. The functions that you're integrated against also have some decay near plus infinity, and you have to make sure that you're never writing plus infinity. So yeah, I mean, I really can't answer precisely why it's.
Does it correspond to a real transition in a way, or is it just technical?
No, it's just technical.
Okay. Any other question in the chat or?
No questions.
Okay. Oh, there's no. Okay. So let's. So well, let's clap then.